We'll be talking about solids and how their atoms and molecules are arranged. So that applies to crystalline solids. Crystalline solids have a long-range order to their atoms or molecules. And when we look at examples of crystalline solids, they often have these beautiful crystal structures. Here's a snowflake, that's solid water, right? And you don't have to do anything special to get the solids to form into these beautiful shapes. That's a result of how the atoms and ions arrange themselves on an atomic or molecular scale. Well, how do we figure out how those atoms or molecules are arranged? An important tool is X-Ray Crystallography. This is a quick review from Chapter 8. Electromagnetic waves can interact with each other. They can interfere with each other. This is true of visible light, but it's also true of all the other different forms of electromagnetic radiation. So if the two waves are in phase, they will reinforce each other and cause constructive interference. If they are out of phase, they will have destructive interference and basically cancel each other out. And we saw a video about this. This was the guy with the big box on the beach with the two slits in it, and the sunlight came through and we saw this pattern of bright spots at the bottom. That's the interference pattern caused by light passing through two slits. An important thing there is that the distance between the slits is similar to the wavelength. So we can use this same idea of interference on a smaller scale. The atoms in a crystal have spacings more like 100 picometers. So that's much smaller, but we can use X-rays, which have smaller wavelengths, to investigate these spacings, right? So here we have an X-ray source, and we focus this beam onto the solid, and as the X-ray goes through this solid, the beams, those waves are going to get deflected and cause interference, and we'll see a diffraction pattern here that reflects what's going on in the crystal. So this is the idea behind this. If we have two rays coming in that are in phase, and let's say this ray bounces off this layer of atoms, and this ray bounces off the second layer of atoms, this ray has gone farther, has traveled farther than ray 1, and that distance is this little bit here plus that little bit there. So this is called A, and that is A, and so the path difference between these two rays is 2A. If that distance is, say, equal to a wavelength, or 2 wavelengths, or 3 wavelengths, then we're going to see constructive interference as a result. So we'll get constructive interference if the difference in the path length is an integral number of wavelengths, just, 2, 3, 17 wavelengths, whatever. And so this basically is geometry, looking at this, and the end result is Bragg's law, where an integer times the wavelength is equal to 2 times the distance between the layers times the sine of the angle of incidence. And so as you shine the X-rays in here, you can vary this angle until you see constructive interference, and then you can calculate the distance between the two layers. So typically what they'll do, like I just mentioned, is they'll look for the angle that gives you constructive interference. And so we can rearrange this equation to solve for D. And X-ray crystallography is very important in studying how atoms and molecules are arranged, both in atomic lattices and ionic lattices, and also things like proteins. So I think most of us know that DNA has a double helix structure. that structure was determined in large part by the use of X-ray crystallography. So here's an example of using Bragg's law. The spacing between layers of molybdenum atoms is 157 picometers. Calculate the angle at which 154 picometer X-rays produce a maximum reflection for n equals 1. So here they're giving us the spacing, which is d, and they're giving us the wavelength, which is 154 picometers, and they're saying n equals 1. And they're asking us, what's the angle? So Bragg's law says that n lambda is equal to 2d sine of theta. So we can rearrange that. Oops, that's not what I want to do. Divide by 2d. So the sine of theta is equal to n lambda over 2 times the distance. Well, n is 1, and lambda is 154 picometers divided by 2 times the distance, which is 157 picometers. Just sticking those numbers in with the units we were given, looking at what happens with the units are going to cancel out, so that means we don't have to convert these into other units at all. So I've got 154 divided by 2 divided by 157. I'll type that in right. Is it? Oh, that's not a good zero. 0.49045. So that is equal to the sine of theta. Sine is a function, so we can't divide by it. We have to do the opposite function, which is inverse sine. So we're going to do inverse sine of both of these. And that tells me that theta is equal to 29.4 degrees. Most calculators have a degree setting and a radian setting, and so if you're not getting the correct number, your calculator might be giving you the answer in radians, which is not what we want. Any questions?